Today we're going to run and analyze hypothesis test for means. For a one sample t-test for a mean, the assumptions and conditions for the one sample t-test for the mean are the same as for a one sample t interval. However, we test the null, the mu is equal to the mu naught, using our test statistic here. Okay, so notice we have t sub n minus 1 equals the sample mean minus the null divided by the standard error of the sample. I typically do not remember the formula with the symbols, because if you write those down on the AP exam and you miss like a bar over the X or you miss a subscript, they will dock you from essentially correct to partially correct. So I always look at the bottom of the first page of our formula sheet where it says test statistic equals the statistic minus the parameter divided by the standard error. In our first example today, we have a classic rock station claims to play an average of 50 minutes of music every hour. However, it seems that every time you tune into the station, a commercial is playing. To investigate the station's claim, you randomly select 12 different hours during the next week and record how many minutes of music the station plays in each of those hours. Here are the data. You would like to perform the test of a null of mu equals 50 and an alternative of mu is less than 50. Where mu is the true mean amount of music played in minutes during each hour by this station. We're going to check the conditions for performing the test to make sure they are met. Real quick, couple of key things we should probably underline. We know it says that it claims to play an average of 50 minutes. That is where we get our null. And we have to use a symbol for mu because average means mean. We also have randomly select 12 different hours, and because you think it seems that every time you tune in this station, a commercial is playing, which implies there's really less music playing than they claim. Remember, our first condition is the random condition, and if we look at the context, 12 hours were randomly selected. Our next condition is the 10%. 12 hours is less than 10% of all hours in 1 week. For our large enough or large counts or condition, there are a couple things we can do. We can have our calculator construct a histogram, and we can check for severe skewness. We can draw a dot plot. We could draw a stem and leaf plot. We just have to illustrate that there's no severe skewness and that the sample is fairly symmetric. So if we look at our histogram here, notice we have no severe skewness. Therefore, we can use a one sample t-test to assume normality. Now, suppose we want to perform a test at the significance level of 10%. Okay, so the first thing we're going to do is we're going to find our one variable stats. Now, how we do that is we put all the data values into list 1 in our calculator, run one variable stats. It should pop up a mean, a standard deviation, and an n. Remember, your degrees of freedom is 1 minus the size of your sample, so in this case 11. When we set up our test statistic, now when we find our test statistic, we insert our sample mean right here. This is my null. The standard error, I take the sample standard deviation divided by the square root of our sample. And be careful when you type it into the calculator. You need parentheses around the numerator when you type it in, and the denominator. And you should get approximately negative 2.57. And here are the one variable stats here. Okay, so notice we have a sketch drawn, and if our t-value was approximately negative 2.57 with 11 degrees of freedom, I can use my chart in reverse to find the p-value. Now, our actual p-value falls in between 0.01 and 0.02 for tail probability. Or what we could do is we could have a t-test run in our calculator. Now, because we have all the individual data values, we can put those into list 1. All we have to do is type our null, that's the mu naught, right? The mu naught, 50, right? 50. List 1, our ha was less than the null, and then we go to calculate. Notice here's our p-value from our calculator, which is really close. It's between 1 and 2%. So you can either use the chart, you can use your calculator. And then all that's left for us to do is to state our conclude. Since our p-value is low, meaning 0.013 is less than 0.10, we have sufficient evidence to suggest the radio station is playing fewer than 50 minutes of music per hour on average. For our next example, we're in the children's game, Don't Break the Ice. Small plastic cubes are squeezed into a square frame. Each child takes turns tapping out a cube of, quote, ice with the plastic hammer, hoping that the remaining cubes do not collapse. For the game to work correctly, the cubes must be big enough so that they hold each other in place in the plastic frame, but not so big they are too difficult to tap out. The machine that produces the plastic cubes is designed to make cubes that are 25.4 millimeters wide, but the width varies some. To ensure that the machine is working well, a supervisor inspects a random sample of 50 cubes every hour and measures their width. The data from a sample taken during 1 hour yield a mean of 25.4154 millimeters and a standard deviation of 0.09 millimeters. Do these data give convincing evidence at the 5% significance level that the mean width of cubes produced this hour is different from 25.4 millimeters? A couple of key things that we need to underline. It says the cubes is designed to are designed to be 25.4 millimeters wide. Notice we have a random sample of 50. We have a sample mean of 25.4154 and standard deviation of 0.09. If I see convincing evidence that tells my brain I need a hypothesis test, I have my 5% significance level, and I have different from 25.4 millimeters. So all those are clues to trigger my brain to do a one sample t-test. Remember our state, we're going to state the hypotheses we want to test and the significance level, and then define any parameters. So our state, we're going to say mu is the true mean width of all plastic cubes produced this hour. Now, if I know they're designed to be 25.4 millimeters, my null is going to be mu equals 25.4, and my alternative, because the question says the mean width of cubes produced this hour is different from 25.4, we're going to use a not equal to for the alternative. For our plan, we're going to identify the inference method and check the conditions. Our inference method is a one sample t-test with a degree of freedom of 49 and an alpha of 5%. It is stated in the problem that the 50 cubes are randomly selected. 50 cubes should be less than 10% of all cubes produced. And for the large enough, because our sample is larger than 30, it is okay to assume it is normal, approximately normal, because of the central limit theorem. Our third step is the do step, and this is where we perform our calculations. Remember, I don't have all the data, but I'm given in the story that the sample mean is 25.4154, standard deviation of 0.09, and n is 50. Remember, we've identified that the t-distribution is going to have 49 degrees of freedom. If we find our test statistic, we take our sample mean minus the null divided by the standard error. And we should get something about 1.21. When I sketch the graph, notice we have the positive 1.21 and we have the negative. And remember, you have to do two sides for a two-tailed test. I can either use my chart for the p-value, but remember, you have to double it because it's two-tailed. Or I can use my calculator and run a t-test in my calculator. Notice we have our null, we have our sample mean, sample standard deviation, how many bigger sample size is, not equal to mu naught, and notice our p-value is 0.232 approximately. Notice we also had the same t-value as if we had calculated it ourselves. Last but not least is our conclude, where we make a conclusion in context. Since our p-value is high, meaning 0.232 is greater than 5%, we fail to reject the null. We do not have sufficient evidence to suggest that the true mean width of all plastic ice cubes produced this hour is different from 25.4 millimeters. Guess what? We finished. No way. The end.